We're going to start talking about some applications of Newton's laws. And one thing that comes up a lot is inclined planes, because it's a little different when we talk about the frame of reference. So remember the three steps that we're always using when we're analyzing force problems. It's free body diagram, frame of reference, and Newton's laws. Now, we've got a situation here. We've got a mass M on a plane that's inclined at an angle theta, and it is moving. It doesn't really matter up or down because we're going to assert which direction friction is. So when we do our free body diagram, the first thing is mg, down, straight toward the center of the Earth. So we take that mass, multiply it by g, and we've got the force of gravity. Then we go around that object and we look at the contact points. And the only contact point is the surface. And there are commonly two forces associated with a surface. One is normal force, perpendicular to the surface. And that makes it a little different. Okay, if it were on a flat surface and it was sliding left or right and nothing touching it, pushing it down, then the normal force would be equal to mg. But in this case, it is absolutely not equal to mg. And then we're going to say it's sliding down the ramp, and so there's a force of friction up the ramp, okay? And so we've got those three things. Now, the thing that we do with this frame of reference is we pick positive directions, two positive directions. We pick our coordinate axes. And in this case, since it's accelerating down the ramp, we really want to pick parallel to the ramp as one of the coordinate axes and perpendicular to the ramp as the other one. So when we do that, it looks like this. And I'll call down the ramp positive and perpendicular to the ramp going up as positive in that direction. You could have those, reversed, doesn't matter. But we do have to pick our coordinate axes. And it's going to make the problem much more solvable if there's only acceleration in one of those directions. If we picked vertical and horizontal, then we would have had acceleration horizontally and vertically downward. So that would make it really hard to solve. So breaking this up now in the frame of reference, remember we have to take any force vectors that don't line up in those coordinate axes. We have to break those down and get the components. And I'm going to show you what the result is. And on the next slide, I'll show you why. But if we break that mg up, what ends up happening is you have a component down the ramp, mg sine theta, and a component into the ramp, mg cosine theta. Mg cosine theta is really, it's pushing into the ramp. If this were a really flexible thing, if this were a pillow, the mg cosine theta is what would compress the pillow, okay? Down the ramp, mg sine theta, that's the thing that's ultimately going to make it accelerate. And honestly, I should have drawn force of friction much smaller. It's not going to accelerate if the force of friction, or it's not going to accelerate down the ramp if the force of friction is bigger than mg sine theta. So now we've got to go to our Newton's laws. The easy one is the y direction, which I'm going to call that, normal force and mg cosine theta. Those are in the y direction, the y coordinate axis. So sum of force equals ma. We write Newton's second law. And this is probably the only time I'm going to do this way. But n is in the positive direction, mg cosine theta is in the negative direction. So we write n minus mg cosine theta equals the mass times the acceleration, which is 0. It's not flying off the ramp. It's not plunging into the ramp. So there's no acceleration in that direction. See how easy that makes it. Now, in the future, I can simply look at that. And it's Newton's first law. It's an equilibrium. There are no other forces in that coordinate axis. So I can say the normal force must be equal to mg cosine theta. I don't always go through Newton's second law to prove that. Sometimes I just say, okay, Newton's first law, it's not accelerating, so I can just say those two. Anything up, total up equals total down is a way of thinking of it. In the x direction, well, we still write Newton's second law. And we do that every time. Why? If there's going to be an acceleration, because it shows the greater that you're actually using physics, okay? So sum of forces equals ma. In the positive direction, it's mg sine theta. In the negative direction, it's ff, so it's mg sine theta plus negative ff, force of friction, equals ma. Then we divide by m, and we would have our acceleration. Now let's do it, excuse me, now let's show why that mg breaks down into mg sine theta and mg cosine theta, where theta is the angle of the ramp. If we look at that as a right triangle, then that angle that you just see there is 90 minus theta, and then right there, the complement of that, the complement of that is theta, right? 90 minus theta. Those have to add up to 90 degrees, right? Because of the 90-degree angle between the coordinate axes. So that makes it a little easier to see. If we then look at the part of that into the ramp, perpendicular to the ramp there, we can see that that's a adjacent leg of a right triangle. So that is going to be mg times the cosine. Cosine goes with adjacent. Cosine of theta. And then the opposite leg of that right triangle is mg times sine of theta. And traditionally, we don't draw it down there. We draw it up there. So that's why they come out as mg cosine theta and mg sine theta. Now, going through this every time is not advised. It's advised to memorize this. And the way I memorize this is a friend was hiking with physics friends, not my friends, but they're hiking, they're walking up the hill, and they're fighting the gravity pulling them down the hill. And one of them said to the other, "Damn mg sine theta." Meaning, I hate having to fight this vector that's pointing down the hill. So if you remember, damn mg sine theta is the part of mg that's pushing down the hill. It makes it really easy. So you can always write mg sine theta. That's the thing that's going to make you accelerate, basically. The other one just pushes you into the hill. Okay, so now let's look at an actual case. It's moving, we've got a force of friction, we've got a mass, we've got an angle. Okay, so mg is 600 newtons, we draw that down. Again, free body diagram, frame of reference, 2 Newton's laws. Excuse me. And if you screw up the free body diagram, you're just out of luck. So the free body diagram is the most critical part here. So remember, the free body diagram is the real forces, and the way we find the real forces is we say, okay, there's a field force, gravity. Everything else has to be a contact force. There is only one contact, and that's that surface. Surface forces tend to be normal force and force of friction. Okay, and I'm going to say it's sliding down the ramp. It could be sliding up the ramp. Friction would be pushing down the ramp. It pushes opposite the direction of motion, as we see when we get into friction. But I'm going to assert that it's up the ramp in this case. So normal, perpendicular to the ramp, friction, in this case, up the ramp. This can be a really complicated problem. I said it's moving because when we get to friction, there's a thing called static friction and there's a thing called kinetic or moving friction. And so it's important to know which one of these. If it were static friction, we wouldn't need Newton's second law. We'd need Newton's first law, where the acceleration is 0. Okay, so now we've got our whole free body diagram. That is the answer. If they say draw a free body diagram, that is your only answer. Okay, I pick my coordinate axes, my frame of reference, and then I break up anything that is not along those lines. A normal force is directly along one of those coordinate axes. Force of friction is along the negative direction of one of those. So we got to break up mg. How do we break it up? Well, the part of mg down the ramp is damn mg sine theta. The part into the ramp is mg cosine theta. So we get that. It needs to be that fast. You really need to be able to do this very quickly. If you're stopping and thinking about all this stuff, you're losing the battle, because this is what I call a canonical problem. In other words, it's a problem that comes up so often it needs to be able to be done in your sleep, because they'll combine it, as we'll see later. They'll combine it with other types of problems, and this needs to be in your wheelhouse. So mg sine theta, 600 sine of 50, mg cosine theta, 600 cosine of 50, and we've got those numbers. And once again, we look at in the y-axis. I can do this in my head. It's not accelerating in the y direction along the normal force axis. So I know the normal force must be 386 newtons. If there were other vectors pointing in that axis, we'd have to take those into consideration, but here it's very easy. Or I could use Newton's second law and solve it. Normal force is 386 newtons. In the x direction, sum of forces equals ma. 460 in the positive direction plus negative 100 equals 60, the mass, the thing that's moving, times a. We divide all that, and we have 360 divided by 60. You get 6 meters per second squared. Positive, that means it's going down the ramp. And once again, I've done a terrible job of drawing the relative sizes of mg sine theta and the force of friction. Force of friction would have to be smaller than 460 newtons. Now let's look at other angled problems. This isn't so bad. This is static. So in other words, we've got this picture hanging on a wall. And if we draw the free body diagram for the picture, we have one wire going up at an angle. I'll call that FT2. That's actually the left wire in the picture, right? And one FT1. That's over on the right side, but pointing up to the left. And I said, let's just, to make it a little more difficult, and I'm not going to solve the whole problem numerically, but to get it a little more difficult, let's say that the right wire, which is FT1, is at an angle of 40 degrees, and the other one's at an angle of 30 degrees, and mg is 20 newtons. That means the mass would have been 2 kilograms. Okay, so what do? We did our free body diagram, we do our frame of reference. No reason to get fancy here. It's not accelerating, so really we could pick any of them. This will probably be the one that's easiest to solve, though. Excuse me. We break up the angled forces. So I'm going to get rid of FT1, replace that with FT1 cosine of 40 and FT1 sine of 40. And then the other one I replace with FT2 sine of 30 and cosine of 30. So you see we have two forces going up. Okay, we need to solve. There's no normal force, there's no surface. Really, it's just gravity, the field force, and those two wires are the only contact forces. So that's my full frame of reference there that allows me to start writing Newton's laws. In the y direction, we have sum of forces equals ma, always write that. Ft1 sine 40 plus Ft2 sine 30 minus mg, which is 20, equals 2 times 0. That's one equation. In the x direction, sum of forces equals ma. We have Ft2 cosine 30 minus Ft1 cosine 40 equals 2 times 0. Mass times no acceleration. Two equations, two unknowns. I'm not going to go into that because it'd be really messy looking. But what you can do is substitute the actual number for sine of 40 and sine of 30 and cosine of 30 and cosine of 40. And you've got a system of two equations, two unknowns. Okay.